talk will be on cryptographic hashing from strong one-way functions or one-way product functions in their applications. This is a joint work between Justin Holmgren and Alex Lombardi, and Alex will give the talk.
Can people hear if I speak like this? Good? Okay. Hey everyone, I'm going to be presenting joint work with Justin, who is somewhere here. I can't see. Oh, there it is. Justin's over here. Very concisely, what we do is we think about two different fundamental black box barriers in cryptography. One of them is proving hardness amplification results for one-way functions.
Can you use the microphone?
Oh, it's no good? Okay.
Yeah.
Does this work? This one? Like this? Okay, okay. So we consider two fundamental black box barriers in cryptography. One of them is proving hardness amplification for one-way functions, and the other is constructing cryptographic hashing. And somewhat surprisingly, we show that these two problems are related. That is, if you can solve the first, then you can solve the second. So for the rest of the talk, I'll explain what that means and how we do it. So any of you who's been through an intro crypto class probably knows we like defining lots of primitives and writing down lots of arrows, meaning if you can solve some problem A, you can solve some problem B. So at the level of secret key cryptography, we have a very nice complexity theoretic landscape, namely a bunch of primitives that are existentially equivalent. If you go beyond that to the world of public key crypto, it's not quite as clean, but we still have a bunch of primitives that definitely imply secret key crypto and appear not to be implied as far as we can tell by secret key crypto. And if you're into postmodernism, we have a little bit more. Namely, we have things that follow from indistinguishability obfuscation. And I'd say the general consensus is that if you have I/O, then you sort of have any cryptographic primitive that you like. I think that's the general consensus. This is a very nice story. It has the minor defect of being a total lie. So there are a few problems with this. The focus of this work is one of those problems, namely collision-resistant hash functions. This is a very pesky primitive. So what's going on? We normally think of it as a very simple cryptographic object, basically living in secret key cryptography land. But unfortunately, while it implies one-way functions and all of these primitives, we have actually strong separations saying that anything on the right-hand side here does not seem to imply collision resistance, at least in a black box way. So the story is a little more complicated in that we actually have a bunch of primitives over here. But the ones that I've written down are all related in some way to collision resistance, and we take collision resistance as sort of the prototypical example exhibiting this difficulty. So the general question is, what's going on here? Can we say anything more, or is there some real fundamental obstacle? So taking a step back for a moment, let's talk about hash functions. So what is a hash function? It's a publicly described and publicly computable function. It takes as input strings, outputs other strings. We often think of it as shrinking. This isn't really required, though. So this is the functionality. Then we need to have some security property on top. So the simplest of these security properties, or the one that you hear about the most maybe, is called collision resistance. It says that given a hash function, it should be hard to find two inputs mapping to the same output. This is one security property. But there's actually a huge family of different security properties of hash functions you could define. And based on various hardness assumptions related to hashing, you get all sorts of interesting applications. So I've listed a few of them here. But essentially, take any cryptographic task you care about, and hashing probably has something interesting to say about it. So we have all these nice applications, but what hash function do you use? This is a huge question. So in practice, we just take an off-the-shelf hash function like SHA-3 and hope it works. And as theorists, this is extremely frustrating. We'd really like some sort of principled explanation for the security of hash functions, I think. And we actually have some tools available. So famously, we have the random oracle model. So what is this? It says that if you take a hash function and model it as if it were a random function, and you model attackers as if they only have query access to the hash function, then you can actually argue security for essentially all of these applications. And so on the one hand, this is great. It gives some evidence for security. But on the other hand, this is clearly an idealized model, and it does not represent reality. In particular, we know that there are some properties of random oracles that no hash function and no family of hash functions can possess. So this leaves huge open question, namely, what properties of random oracles can we actually instantiate with real functions? and under what hardness assumptions can we instantiate these objects. So going back to just this one example of collision resistance, we can ask, take any of your favorite cryptographic primitives, like one-way functions, say even extremely strong one-way functions, or even crazier things like our postmodern obfuscation. And can any of these imply collision resistance? And unfortunately, we know that we can't. It's really unfortunate. This does have the caveat that these impossibility results are for black box constructions, but on the other hand, we also don't have any non-black box constructions in this line of work. So I'm going to talk about just the first of these impossibility results. It's due to Simon from 1998. So what it says is that there's an oracle relative to which extremely strong one-way functions or even one-way permutations exist, but collision-resistant hash functions do not. And so by extremely strong one-way permutation, I mean a one-way permutation which any polynomial time algorithm cannot invert with probability essentially any better than guessing an input at random. You can get something that strong. So this is an extremely strong impossibility result. And this leaves the question, well, what do we do now? We have this really strong impossibility result. Can we do anything? So option one is just to give up and go home because it looks pretty scary. And this is a very tantalizing option, actually. But assuming we don't want to do this, what we can try to do is prove that this oracle separation is unrealistic somehow. What would that mean? That would mean identifying some property of one-way functions that we expect to have that does not hold in the oracle world. That would be an interesting thing to do. So one thing that we do is we actually do option two. So I'm going to describe a property that we should expect to hold for one-way functions but doesn't hold in the oracle world. So take any function f that you like. Imagine that you're given now two outputs, y1 and y2, corresponding to some inputs x1 and x2. It turns out in Simon's oracle world, it is always possible to recover both x1 and x2 at the same time with probability 2 to the minus n. So this is surprising because randomly guessing only gives you 2 to the minus 2n probability. So there's an exponential improvement here over the trivial algorithm. And if you think about it, you can say more generally that no matter how easy or hard f was to invert originally, you can actually invert f twice with the same probability that you can invert f once. And this is crazy. This doesn't make any sense at all. You shouldn't be able to do that. So what we do in this work is we actually formulate that as a hardness assumption. So we define this problem of double inversion. It's parameterized by some function, efficiently computable function f. The computational problem is you imagine that you're given now two outputs, y1 and y2, that come from two independently random inputs, x1 and x2, and yi is f of xi. So you're given these two outputs. Your goal is to invert f on both of these outputs at the same time. And the hardness assumption, which is parameterized by some probability delta, is that you succeed at this with probability at most delta. So the parameter regime of interest here is when delta is less than 2 to the minus n. That is when delta is less than the probability of just guessing one of the two inputs at random. And so I personally think of this sort of delta security as a version of square root of delta security for the function f that is robust, in the sense that in addition, there's no way for an efficient adversary to somehow correlate solving one instance of the problem to solving another instance of the problem. So there's an intuition that comes up in parallel repetition all the time. So here's, okay, great. So I've written down a hardness assumption. Sort of by construction, you can't have such a function in Simon's oracle world. I sort of defined it so that it's not possible. But on the other hand, great. This is actually useful. So somewhat surprisingly, it turns out if you have a one-way function satisfying this sort of hardness, you can actually construct collision resistance. So this didn't just, in a contrived way, avoid Simon's impossibility. It actually avoids the black box separation entirely. So that was the simplest result, or the first result in our paper. Now I'll describe a little more methodically what we do. So the first thing we do is we define a new notion, or an extension of a one-way function, which we call a one-way product function. So it's sort of a generalization of this double inversion hardness I described in the previous slide. So more generally, you could imagine having k functions and asking about how hard it is to invert all k of them at the same time. so we define these notions, and because it appears that nobody has really studied this or formally studied this in the past, we actually take a lot of time to consider different notions, different variants, talk about how they're related to each other, and sort of establish some foundations. And I think this is an important part of the work. So after doing this, we actually show that these one-way product functions are useful. Namely, they imply various forms of hashing that we know one-way functions do not imply. So the collision resistance result is one such result. So more generally, we obtain this notion called output intractability. So while collision resistance says you have a hash function where it's hard to find two inputs mapping to the same outputs, output intractability says something like it's hard to find two inputs or even k inputs whose corresponding outputs satisfy some relation which is typically not satisfied, which is rare. And you can formulate this for any sort of relation. You can ask, is there a hash function where this is hard? And so we construct output intractability for any such relation from one-way product functions. So even more generally, you can consider this sort of correlation intractability, where you have a relation that takes as input both the inputs and the outputs, and we obtain some sorts of results along these lines as well, but I'll defer to the paper to precisely state what we do. So we have all these hashing constructions, and as a corollary, we actually get a possible approach for avoiding Simon's impossibility result for constructing hashing from one-way functions. And I'll describe in a little bit more detail in a bit what I mean by this. So, but for now, let me actually define the object that we defined. So a one-way product function is a k-tuple of functions, f1 through fk, or more generally, you could imagine having a distribution on k-tuples of functions. And they should be efficiently computable in the forward direction. And we have an associated hardness assumption that says it's hard to invert all k of the functions at the same time, or hard in the sense that any polynomial time adversary should not invert with probability better than some delta. Again, delta should be less than 2 to the minus n for this to be interesting to us. And again, we think of this as sort of a delta to the 1 over k kind of security, where we additionally assume that there's no funny way to correlate solving independent problems. That's the assumption here. So that's the definition. Then you can ask, well, can we actually write down objects that satisfy the security property? So one possible avenue for doing this is writing down concrete candidates. And there are actually problems previously studied in the literature that appear to give one-way product function kinds of assumptions. In particular, in the generic group model, discrete log problems give this sort of hardness assumption. So concrete candidates is one approach. But the other is there's actually a possible generic approach for getting one-way product functions from one-way functions. And the idea would be take any one-way function you like, just repeat it k times, and you can ask, well, is this a one-way product function? And the question of whether or not this is secure is exactly the question of whether parallel repetition exponentially decreases the probability of inversion. That's what we're asking. So a classical result due to Yao says that parallel repetition decreases this inversion probability to an extent. But on the other hand, we actually have a counterexample saying there is some one-way function which does not give you an exponential decay. But on the other hand, this is a fairly contrived counterexample. It seems like any natural function you write down should give you this exponential decay. And so personally, I actually think you could have the following sort of approach to getting parallel repetition. You can imagine starting with any one-way function. It itself may not give you exponential decay, but you could imagine making a modification to the function f that gives it this exponential decay when you repeat in parallel. This would be a super interesting result. Why? If you could do something like this, then you could actually get collision resistance from one-way functions in the following sense. You could start with a very strong one-way function. You could apply this modification to get a one-way function whose hardness does repeat in parallel, and then by the work that Justin and I do in this paper, you would then get collision resistance. So this would actually bypass Simon's impossibility result in a very strong sense. So I think it's an extremely interesting question whether or not something like this is actually possible. So in particular, we know very little right now on under what conditions on a function f you can actually get this sort of exponential decay in parallel repetition. I think this is a super interesting question that we should think about more. So with all of this context in mind, I'm now going to describe our result again. So this is going to be a graph about the hardness of one-way product functions. So first of all, ordinary one-way functions care about the probability of inverting one challenge. And they can be at most 2 to the minus n secure because you can just guess the input at random. In general, a k inversion problem can be at most 2 to the minus kn hard. So Simon's impossibility result says that one-way functions with essentially any inversion probability cannot in a black box way give you collision resistance. Our collision resistance result says that if you consider the probability of inverting 2 challenges, if you have any hardness better than 2 to the minus n, you get collision resistance. So as an example, one of our other results is that if we consider the problem of k collision resistance, so what is this? It's the problem of finding k inputs mapping to the same output. It turns out if you start with a k one-way product function whose hardness is any better than 2 to the minus n, then you get k multi-collision resistance. So I'd like to point out that this assumption on the right is much weaker than the double inversion hardness assumption because I'm asking for only 2 to the minus n probability with k repetitions as opposed to 2. So it's a much weaker assumption. More generally, what we show is that any k one-way product function whose security is above this line is useful for constructing some hash functions that one-way functions do not give us. Because in particular, Simon's impossibility result actually says that anything below the line is useless. So we give a converse, essentially. We say anything above the line is actually useful. So with my remaining time, what I'll do is outline the simplest of our constructions and security proofs, the simplest being the collision resistance result. So again, I'll state the result. And for the purposes of this talk, I'm going to stick with injective functions just so everything is simpler. So the theorem statement here is that we have an injective function whose double inversion hardness is better than 2 to the minus n. Then we get collision resistance. So by the way, we can actually make this more quantitative in that if you have a significantly better than 2 to the minus n hardness, you get a significantly better than ordinary collision resistance. You can scale it up as far as you want. In particular, if you have an optimal 2 one-way product function, you get an optimal collision resistant hash function. So very quickly, I'll describe how it works. So the construction is extremely simple, and the idea is back from the 80s. Namely, take your function f, post-compose with a pairwise independent hash function. Extremely classical result. But this is the construction. The question is how you prove security. This is the interesting part. So here's the reduction. Suppose you have an adversary breaking collision resistance of this hash function. What does it mean? He gets a pairwise independent hash function, and he produces some 2 inputs x1 and x2, such that p of f of x1 is equal to p of f of x2. We now want to use this adversary to break the OWPF assumption on f. So here's how we do it. The OWPF assumption says, hey, we're going to get 2 random outputs. That's y1 and y2. So here's how we invert. We're going to sample a pairwise independent hash function p, but not a uniformly random one. We're going to sample one conditioned on the event that it maps y1 and y2 to the same output. Then we'll feed this to the collision finder and just hope that he straight up solves our problem. Hope that he produces x1 and x2. That's the whole reduction. So why should that work? The idea is that what this sampling is doing is we're somehow planting a random collision inside the pairwise independent hash function. The way the argument goes is we say that the adversary can't tell which of the collisions in this P is the one that we planted. And so if he can actually find any collision with noticeable probability, then there will be a better than trivial probability of him finding our collision because he can't tell which collision we actually planted. So this will actually show that we can actually invert y1 and y2 with probability 2 to the minus n as opposed to 2 to the minus 2n, and that violates the assumption. So I know it was fast, but I just wanted to give a sketch of the security proof, and this is how it works. So to conclude, what do we do in this work? We get a clean instantiation of random oracle properties in the standard model, as with actual hash functions, and we actually get a very nice quantitative security on top, such that we can even hope for an optimal security under a certain assumption. So this is very nice. How do we do it? We define this notion of a one-way product function, which is a generalization of one-way functions, talking about some sort of multi-instance security. And we think of this as a very clean assumption. we think of it as a reasonable assumption, and it turns out to actually be useful in cryptographic constructions. So, and finally, it actually also gives us a possible approach to avoiding some black box impossibility results in cryptography related to hashing by relating it to the problem of hardness amplification for one-way functions. And I think this last question is extremely interesting that I hope the community thinks about a little more in the future. Thank you.
Questions for Alex?
Absolutely, yeah. So on the other hand, you could imagine a variant where, if you have trapdoor functions, you have a family, right? So you could imagine instead sampling many functions from the family independently. And then again, it's plausible. And this is also something that we can work with here. Right. So, yeah. So if you have a single function, this can't come up. And if you have a family of functions, morally the right thing to do is do this independent sampling. Yeah.
I'm sorry if it's a well-known thing, but how do you invert a function on 2 points with probability 2 to minus 9?
No. So this shouldn't be possible. So I think maybe you were talking about when I was about the like in the oracle separation. No. So the point here is that Simon writes down a very strange world where this is possible. Yeah, it's possible in the sense that there's. yeah. That's exactly the point. This is absurd. We should not expect this. Yeah.
Further questions? Actually, do you have any thoughts about what sort of fortification might be plausible?
It's a good question. I don't really know. Somehow it seems like people haven't thought of, or at least I haven't found very much work on it. Or fortification is a thing that's come up in like somehow other kinds of parallel repetition, but not in this like one-way function setting at least, right? So that's as far as I know.
Interesting. All right, let's thank the speaker then.